Okay, today we're going to look at periodic and symmetry identities. And in order to do that, we're going to explore the value of some trigonometric expressions. So first we'll look at sine of 11 pi over 6. It may be helpful for us to draw this. Sine of negative 11 pi over 6 indicates a clockwise direction angle, and that's just a little bit less than 12 pi over 6, or 2 pi. It's less by pi over 6, or 30 degrees. So if we want to think about a 30-degree reference angle, where that terminal side intersects the unit circle is the point square root of 3 over 2 comma 1/2. So that means that the sine of negative 11 pi over 6 is the second coordinate, or 1/2. Similarly, we can draw an angle of pi over 6. That's a counterclockwise angle. Reference angle will be, again, 30 degrees. And so the coordinates of the point where that terminal angle intersects the unit circle are square root of 3 over 2 comma 1/2. So the sine of that angle is equal to the second coordinate, positive 1/2. And if we look at an angle of 13 pi over 6, that's more than 12 pi over 6, or more than one full rotation. Positive angles rotate in a counterclockwise direction. So our terminal side is, again, 30 degrees displaced from our initial side. And the coordinates are, again, square root of 3 over 2 comma 1/2. And the sine of that angle is equal to positive 1/2. All of those expressions have the same sine value, and the angles all differ by 2 pi, which happens to be the period of the sine function. Let's take a look at some expressions involving the tangent function. Tangent of negative 2 pi over 3. That's a clockwise direction angle. And that's 60 degrees short of a half turn. So that's a 60-degree reference angle. The coordinates of the point where the terminal side intersects the unit circle will be negative 1/2 comma negative square root of 3 over 2. The tangent is the second coordinate over the first coordinate. So the value of the tangent is positive square root of 3. Now let's take a look at tangent of pi over 3. Pi over 3 is a 60-degree angle, so our terminal side will be in quadrant 1. And the coordinates of the point where the terminal side intersects the unit circle are positive 1/2 comma positive square root of 3 over 2. The tangent is the second coordinate over the first coordinate, which is positive square root of 3. And lastly, let's draw 4 pi over 3. 4 pi over 3 is a counterclockwise direction angle. 4 pi over 3 is pi over 3 greater than a half turn. So that again gives us that 60-degree reference angle. Coordinates of the point where that terminal side intersects the unit circle are negative 1/2 comma negative square root of 3 over 2. The tangent is the second coordinate over the first coordinate, and so the tangent is, again, positive square root of 3. All of these angles differ by pi, which happens to be the period of the tangent function. Please change this typographical error in your notes to the word tangent. So that leads us to the periodic identities, which say that if I add or subtract 2 pi from an angle in an expression that has a period of 2 pi, then the sine values, the cosine values, the cosecant values, the secant values are the same. For tangent and cotangent, the period of those functions is pi. So it's important that we recognize that those periodic identities are slightly different. So we can use the periodic identities to rewrite expressions so that we are taking the cosine, sine, or whatever trigonometric function of the smallest angle possible. So for a cosine function, I can add or subtract 2 pi and have the same value. So 2 pi for this angle would be 10 in the form 10 pi over 5. If we subtract that off from the angle that's given, we'll have cosine of 7 pi over 5. And that's the smallest angle possible, smallest positive angle possible. Because if we subtracted another 10 pi over 5, the angle would be negative. The next one is a tangent function. And for a tangent function, we can subtract off any multiple of 1 pi. So that means 7 pi over 7, 14 pi over 7, 21 pi over 7, etc. The biggest multiple that we can subtract off is 35 pi over 7, which is equivalent to 5 pi. So if we subtract that off, we can rewrite this as the tangent of 3 pi over 7. Cosecant has a period of 2 pi. So for this one, we're going to need to add 2 pi in the form 18 pi over 9. And re-express this as cosecant of 16 pi over 9. In D, we have a cotangent function. And remember that cotangent shares the same period with tangent. So we can add any multiple of 1 pi. Well, a multiple of 1 pi is 9 pi over 9. So we can rewrite this one as the cotangent of 7 pi over 9. Now I've put parentheses around the angle. Sometimes you'll see parentheses around the angle, sometimes you won't. Generally speaking, we always put it there if the angle is negative. Sometimes when the angle is positive, we may leave it off. Okay, in E, we're dealing with a tangent function, so we're going to subtract off any multiple of pi. That would be 8 pi over 8, 16 pi over 8. And I think 16 pi over 8 is the biggest multiple that we can subtract off and still have a positive angle left. So rewriting this one will be the tangent of 3 pi over 8. The object here is not to evaluate these, but rather to re-express each expression as a trig function of the smallest positive angle possible. Okay, in F, we have a sine function, and sine has a period of 2 pi, so we're going to subtract off 2 pi in the form 20 pi over 10. We can't subtract off 4 pi because that would be 40 pi over 10, and then we'd have a negative angle. So that gives us sine of 11 pi over 10. Okay, in example 2, we're going to evaluate two trig expressions. Sine of pi over 6 and sine of negative pi over 6. Now you may find it helpful to draw these. If we draw an angle of pi over 6, the coordinates in the unit circle are the square root of 3 over 2 comma 1/2. If we draw negative pi over 6, and the coordinates on the unit circle are square root of 3 over 2 comma negative 1/2. So that tells us that the sine of pi over 6 is 1/2, and the sine of negative pi over 6 is negative 1/2. Okay, let's do the same thing with cosine. We can use the very same diagram. Cosine is the first coordinate, so cosine of pi over 6 is square root of 3 over 2, and cosine of negative pi over 6 is also positive square root of 3 over 2. So this text tells us actually something that we call the even and odd identities. Sine of the opposite of theta is equal to the opposite of sine of theta. Because you'll notice that sine of pi over 6 and sine of negative pi over 6 have opposite values. Cosine of negative pi over 6 and cosine of pi over 6 have the same value, so that tells us that cosine of the opposite of theta is the same thing as cosine of theta. We call these the even and odd identities. We'll go into more detail about that terminology. But if you remember that what the graphs of sine and cosine look like, we can observe the same thing about them through looking at the graphs. So in the graph of sine, if we look at that and we call the sine function f of x, so f of x would be equal to, or rather, sorry, f of theta would be equal to sine of theta. Then f of the opposite of theta, we can see from the graph, has an opposite y value, so it's the opposite of f of theta. For the graph of the cosine, let's call this one function g. So g of theta is equal to the cosine of theta. And if we look at points on the graph that have opposite theta values or opposite input values, we can observe that they have the exact same y value. So g of the opposite of theta is equal to g of theta. We can use these two ideas about the symmetry of the sine and cosine functions in order to find out what the symmetry of all of the other 4 trig functions are. So cosecant of the opposite of theta can be re-expressed using a reciprocal identity as 1 over the sine of the opposite of theta. Well, we know that sine of the opposite of theta is the opposite of sine of theta, and this is the opposite of sine of 1 over sine of theta, so it's the opposite of cosecant of theta. So this would have the same symmetry as the sine function. And by the way, we're going to call the sine function an odd function, so that makes the cosecant function also an odd function. Now let's take a look at secant. Secant of the opposite of theta is 1 over the cosine of the opposite of theta. Cosine of the opposite of theta is the same as cosine of theta, so that's equal to the secant of theta. So secant of the opposite of theta is equal to secant theta, which makes the secant function have the same symmetry as the cosine function. By the way, we're going to call the cosine function symmetry even, so that makes the secant function also an even function. Okay, now let's take a look at tangent. Tangent of the opposite of theta is equal to the sine of the opposite of theta over the cosine of the opposite of theta, which is equal to the opposite of the sine of theta over cosine of theta. Well, that's equal to the opposite of sine of theta over cosine theta, which is the opposite of the tangent of theta. Since tangent of the opposite of theta equals the opposite of tangent of theta, that makes the tangent function an odd function. Opposite inputs give opposite outputs. For the cotangent function, cotangent of the opposite of theta is equal to cosine of the opposite of theta over sine of the opposite of theta, which is cosine of theta over the opposite of the sine of theta. That gives us the opposite of cosine over sine, which is the opposite of the cotangent function. Since the cotangent function yields, since an opposite input for the cotangent function yields the opposite y value, the cotangent function is also odd.